I'm Rutha and Amanda, and welcome to the premiere episode of Rutha and Amanda presenting Fun with Fiber Optics. Over the next 8-ish minutes, you and I are going to explore the dynamic world of fiber optics. Fiber optics are a way to transmit light signals quickly and efficiently over great distances. They are made up of 3 layers, which include the core, which is made of glass, the cladding, and a protective buffer coating. Think about a flashlight shining down a long hallway. What if the hallway had a bend in it? Light can be reflected off of a mirror that is placed in the corner. The walls can also be lined with mirrors, and that would allow the light to bounce off side to side. This is precisely what happens in optical fibers. Fiber optics are important in many aspects of industry, including computer networking, telecommunications, remote sensing, medical imaging, and power transmissions. Fun fact, underneath the Atlantic Ocean, a fiber optic cable connects Europe to the United States of America.
To understand fiber optics, one must understand the principles of reflection, refraction, and dispersion. Reflection occurs when light is bounced off of a surface rather than being absorbed. We are able to see the moon at night due to the sun's rays being reflected off of the moon. Within the aspects of reflection, a phenomenon known as total internal reflection takes place where the angle of incidence is greater than the critical angle. This is the angle of incidence, and this is the angle of refraction. The critical angle is the same as the angle of incidence whenever the angle of refraction equals 90 degrees. Refraction occurs when a wave is bent moving from one medium to another. This can be seen when you're looking at a glass of water with a straw in it and the straw appears to be bent or broken. Another example is when you drop a fork into a tub of water. From above, it looks like it is in one position, but really it's in another. The refractive index is the ratio of the velocity of light in a vacuum to its velocity in the specified medium. So we're going to look at an example of how to solve for the index of refraction. Light travels through a liquid at 2.25 times 10 to the 8th meters per second. What is the index of refraction of the liquid? The speed of light in a vacuum is 3.0 times 10 to the 8th. So we're going to come over here and we're going to write the equation. N is equal to C over V. So the speed of light in a vacuum is 3 times 10 to the 8th. And we're going to divide that by 2.25 times 10 to the 8th. And that is going to give us 1.3 as our index of refraction.
In relation, the refractive index is used in calculating Snell's law, which relates the proportions of the angles of incidence and refractive indices of 2 mediums. Snell's law states that n1 over n2 equals sine theta 2 over sine theta 1, where sine theta 1 represents the angle of incidence, sine theta 2 equals the angle of refraction, and n represents the refractive index. Let's try a few examples. So here's an example of an application of Snell's law. A ray of light traveling from air to crown glass strikes the surface at an angle of 30 degrees. What will be the angle of refraction? So the first thing to do is to acknowledge Snell's law. The known values are the refractive indices and the angle at which light strikes a surface. In order to find the angle of refraction, rearrange Snell's law to solve for sine theta 2. In order to solve this equation, the numbers would have to be plugged in by multiplying 1, which is the index of water, with the sine 30 degrees, and dividing it by the refractive index of the crown glass, which is 1.523. By doing this calculation, the angle of refraction turns out to be 19.2 degrees. Let's try another example.
What is the angle of incidence for a light ray traveling from water into flint glass if the angle of refraction is 30 degrees? So we have to look at the refractive index of water, which is 1.33, and the refractive index of flint glass, which is 1.70. So we're going to come over here and write out the equation first. N1 over N2 is equal to sine theta 2 over sine theta 1. So the refractive index of water is 1.33. And we're going to divide that by the refractive index of flint glass, which is 1.70. And this is going to equal the angle of refraction, which is 30 degrees over the angle of incidence, which is sine theta 1. So 1.70 times sine 30 degrees is going to give you 0.85. And you're going to divide that by 1.33 and find the inverse sine of that value, which is 0.639, which gives you an answer of 39.7 degrees, and that is your angle of incidence. Now we're going to move on to dispersion. Dispersion describes the phenomenon of light scattering where the phase velocity depends upon the wave frequency within the medium. This is most commonly seen in the scattering of light through a prism. The white light is separated or dispersed into red, orange, yellow, green, blue, indigo, and violet light.
Now that the fundamental concepts behind fiber optics are understood, let's move on to a couple of the applications of fiber optics. Fiber optics are used for a number of different purposes. They are very versatile. They are used in telecommunications and computer networking to transmit over a terabit per second. That is the amount needed to make 13 million phone calls simultaneously just within one fiber. They also provide increased security so that hackers cannot easily access vulnerable data. Fiber optics have immunity to electromagnetic interference, and this allows them to have optimal data security without significant loss of data through transmission.
Optical fibers are also used extensively in the medical industry. They can be used in medical imaging, such as catheter endoscopes, which can have up to 10 micrometer resolution. They are also used in biosensors, such as this picture shown, which monitors glucose levels. Optical fibers can be seen in dental instruments as well, such as this dental illuminator. Overall, fiber optics prove to be the technology of the future because they have applications in many fields, from telecommunication to medicine. They are flexible, secure, non-flammable, low cost, and have low energy degradation. Fiber optics will soon replace copper wiring due to their many benefits and high efficiency.